Throughout history, astronomers and observers of the sky have acknowledged that the stars scattered across the heavens display an incredible diversity in appearance. So much so that the naming of individual stars has been found throughout ancient civilizations and was used to tell stories, mark the time of historical events, and map changes seen in the heavens. When looking at the stars, the two most easily observed traits are their variety of brightnesses and their colors. Even to the unaided eye, the difference in brightness between the brightest and the faintest stars is over a factor of 600. The colors of stars can also provide dramatic distinctions. Stars are not all simply white points of light, but instead can be bright orange or reddish, yellow like our sun, or a bright bluish white. The color of a star corresponds with its surface temperature, similar to how the color of a fire's flame shows how hot the fire is. If a star is very hot, it will appear blue-white, while on the other hand, a cooler star will be red in color. Of course, stars are not exactly like the flames of fire we usually see. Instead, the objects we call stars today are extremely dense collections of gases, mainly hydrogen and helium. These intensely hot bodies of plasma emit tremendous amounts of energy, some of which is visible light. Despite fundamental similarities, the diversity of stars is astounding. In the late 1800s, Annie Jump Cannon, a female astronomer at Harvard, painstakingly worked to classify approximately 400,000 stars into a systematic framework. Today, the basis of her work can be seen in the stellar type designations using the letters O, B, A, F, G, K, and M. Listen to how she described her work and what significance it would provide. Classifying the stars has helped materially in all studies of the structure of the universe. No greater problem is presented to the human mind. Teaching man his relatively small sphere in the creation, it also encourages him by its lessons of the unity of nature, and shows him that his power of comprehension allies him with the great intelligence overreaching all. The work of Cannon, Pickering, and their contemporaries helped to quantify how truly diverse stars really are. Building upon their success in surveying stellar types, two early 20th century astronomers, Hertzsprung and Russell, began to see amazing relationships when comparing the spectral types Cannon had developed with the absolute brightnesses of the stars. When they plotted the spectral type against its absolute brightness, distinct groupings of stars became apparent. Today, these groupings generally categorized into the following classes: dwarf stars, main sequence stars, giants, and supergiants. Within each of these groups, there are sub-classifications that distinguish even more of their stellar complexities, such as white dwarfs and red dwarfs, red giants and blue giants, and numerous types of variable stars. This classification chart continues to be an important tool and is referred to as the Hertzsprung-Russell or HR diagram. When you look at the HR diagram, probably the first pattern you notice is that most of the stars form a diagonal line across the plot. This grouping is called the main sequence and provides an interesting relationship that simply says hot stars are generally brighter than cool stars. Exceptions to this rule do exist, and when studied, we find that they often have some extreme characteristics. Main sequence stars are often considered as the more usual or typical group of stars, and our Sun is located about in the middle of this main sequence. White dwarfs are stars that fall well below the main sequence line, and like their name suggests, their radius is small, being about the same size as Earth's radius. However, their white color tells us that they have a very hot surface temperature. On the other hand, giant stars are larger and brighter than those on the main sequence. On the HR diagram, you will find these stars above the main sequence line. Supergiant stars, as their name indicates, are even bigger than giant stars. The largest stars are typically supergiant stars that can be upwards of thousands of times bigger than our sun. But because of their red color, they have much cooler surface temperatures. If you were to look in the night sky at the constellation of Orion, you would see a bright red supergiant star. Orion is often one of the most obvious constellations to identify, and it can best be seen during the winter months in the northern hemisphere. One of the easiest ways to identify Orion is by locating the line of 3 relatively bright stars that form Orion's belt. Once you have located the 3 belt stars, the red supergiant star is located up and slightly to the left, about where you would expect Orion's right shoulder to be. This star, named Betelgeuse, will appear as one of the brightest stars in the Orion constellation. If you were to place Betelgeuse into our solar system, right where the Sun is, it would extend outward beyond Jupiter's orbit. If you continue looking at the constellation of Orion, but this time look towards the bottom right, about where Orion's foot might be, you'll see a blue star called Rigel. This star is a blue giant, which means that it is much larger than the Sun and also has a surface temperature about 11,000 Kelvin, many times hotter than our Sun. Thinking back to the HR diagram, both of these stars will be well above the main sequence line in the giant and supergiant regions. However, due to their vastly different colors, they will be at opposite ends of the temperature scale. In 1 Corinthians chapter 15, the Bible uses the great diversity of stars to teach a spiritual lesson about our souls. It says, "There is one glory of the sun, another glory of the moon, and another glory of the stars. One star differs from another star in glory." The Christians in Paul's day could easily understand this analogy. Today, we also can understand it, and maybe even to a greater extent, as we see how diverse, ordered, and designed the stars in our universe really are.